With the mask on? Okay. Okay, so Gregor got through the beginning of generative modeling and introduced the concept of a GAN. Next on the list, going that way, would be something called a variational autoencoder. And I guess the way we split it up, we'll just take a slight detour right now, or just talk about another approach to the problem, which goes by the name of normalizing flows. And before I introduce what a normalizing flow is, let me talk in broader terms about the problem that normalizing flows are trying to solve. Okay? And it is related to generative modeling, but it's also different. So that's what we talked about. We did go over this a little bit in the first lectures. So let me just start with a general introduction to the problem of density estimation and generative modeling. Well, and its connection to generative modeling. Okay, so remember we said in the first lecture that there's a general class of problems where you might be given some data X, and you want to learn, so learn the underlying probability density that X is drawn from, okay? And X could be very high dimensional, and that's the challenge, okay? So this is an old problem. So this is density estimation, the task of density estimation. And I think people have been trying to do this for a long time. And some of the classical approaches, I'm not going to spend hardly any time on these. I just want to briefly flash a couple of classical approaches in front of you, just so that you can appreciate how revolutionary, hopefully, or like science fiction-y the modern machine learning approach of normalizing flows is compared to this. Okay, so one classical approach to density estimation that maybe you've heard of before goes by the name of kernel density estimation. Okay, and it's based on the idea that one very dumb approximation to this data is that every data point represents a delta function, right? So that could be the density, all right? It could be that phi of x is equal to the sum over delta x minus xi, I from 1 to n data, right? It could be that that's the density. How would we tell that this is a bad approximation to the density? How would we know that this is not a good density? Sorry, maybe I should put a 1 over n here. So if someone said, this is my guess for the probability density, how would you tell them that this is probably not a good guess? Or how would you check that? Oh, no, so it integrates to 1, right? It integrates to 1. That's why I put the 1 over n data here. The integral over this is normalized to 1. So it's not a mathematical thing. So how would I tell, like empirically, that this is not a good density? Yeah? The derivative, okay, well, yeah, so the derivatives are very singular, but let me not worry about that either. But good tries. Yes? Right, so, okay, so this is like massively overfitting the answer, right? So implicit here is the idea that, so let's say I fit it to this data, right? But then maybe there's more data, okay? If there's more data, it follows the same distribution, right? but it's not exactly those data points. It's drawn from the same distribution, but it's not exactly the same points anymore. Then what is my density going to be on all the new data points? Exactly 0, right? So it's a terrible approximation to the truth. Okay, so I'm assuming here that this data here is the training data, and then I have more data that I'd like to really use this on, right? Okay, so good. So this is a bad answer. Doesn't generalize. Okay, so the idea of kernel density estimation is to say, let's suppose this is still some kind of guess, okay, and we just like smooth it out. Okay, let me blow up the delta functions. So around every point where I have data initially, I just imagine I draw like a little ball around it or something, and say that's my density estimate. Okay, so KDE is just to say we replace the delta functions with some kernel, okay, and that kernel function is a choice you can make. But probably you want the kernel function, you know, to be smooth and fall off. It should be normalized to 1, just like a delta function is. But yeah, so that's the idea of KDE. And you might choose, for example, you might choose kernel function, which is Gaussian, right? So you might choose a Gaussian kernel. That's a very common choice. And so yeah, you should just think of this as given the data and given the initial guess of delta functions, just smoothing it out. Okay. So the upside to KDE, the advantages of KDE is it's very fast to implement, right? It doesn't scale well with the data. Okay, so pros is that it's easy to implement. I would say the cons are that if you literally tried this with, say, 1 million data points, this sum starts to become hard to evaluate. So it doesn't scale well, doesn't scale well as n data goes to infinity. I mean, obviously, you know, it's a very strong restriction to put on your density estimator to say every single point is represented by the same kernel, right? That's clearly a strong assumption. Okay, so another con is that it's not very expressive, okay? There's a very strong sort of inductive bias here. And then I'd say one more disadvantage that you can think of, that I could think of, is that, well, let's see. I guess, okay, if I did it with Gaussian kernels, well, yeah, let me not, I think, I'm a little confused now, whether I can sample from this KDE or not. I guess I probably could sample from this KDE. Okay. But anyway, so it's not a very good density estimator because I think assuming every point is really a Gaussian ball of the same radius is too strong of an assumption in practice. Okay, so what's another classical approach to density estimation? Something called Gaussian mixture models. You might have heard of before. It's to say, let me write down, okay, so people like to say that KDE is non-parametric. When I think that's a bit of a lie because there is a parameter here. They call this the bandwidth parameter. But anyway, they like to say that KDE is non-parametric. So an example of a parametric model is where I say, suppose my data is somehow, you know, described by or can be fit to a superposition of Gaussians. Okay? So we would say my model for the data looks like this. It's just the sum. I guess it also depends on the normalizations. Sum of NA e to the minus x minus mu a squared over 2 sigma a squared. Okay? And it's up to me how many mixtures I include, how many Gaussians I include. Okay? So this is to say maybe the data is well modeled by just a superposition of different Gaussians centered at different places in my data space, okay? Good, so now this is a model of the data. It might not be a very good model, okay? But it is a model of the data and it has these parameters. So what am I supposed to do? I'm supposed to fit these parameters to the data, right? And so how should I fit these parameters to the data? Based on what we've learned in the first lecture or in the earlier lectures? Good. So what we should do in this case, and that's I think the nice thing about density estimation, or at least parametric density estimation, is that the problem we're trying to solve, which is learn the likelihood function of the data itself, that actually makes the minimization or the optimization completely immediate, like what it is, it's completely transparent, like what we're supposed to do, right? So we want to minimize minus the loss, which is minus log p summed over the data, I equals 1 to n data. So we want to minimize this with respect to the parameters of the model. Okay, and we didn't have to work hard at all. Like we didn't have to derive like we did the binary cross entropy, right? This one just is pretty automatic. Like this is what we should do. Okay, good. And yeah, so I think this is actually a key insight, which is going to carry over. This is going to carry over to when we do normalizing flows in a second. Yeah. Is this a special case of KDE? No. No, I would not say that, because here these centers are allowed to be anywhere. Oh, okay. Yeah, so good. I've had this confusion myself too before. So KDE, the centers are not free parameters. That's why they call it non-parametric. It's every data point is a center. So if anything, KDE is a special case of this, where I put it, yeah, actually you could think of that, where the number of mixtures is the number of data points. These centers and these sigmas are not allowed to vary, and these NAs are all 1. So KDE is like a very special case of this. Good. Okay, so again, this is a model. It might fit your data well, or it might not. Okay, so again, the pros is that this is it's as easy to implement in general. Cons is that it's not very expressive. Okay, good. Let me mention one other, okay, let me call this a semi-classical approach. And it actually solves a slightly different problem. It's called mixture density network. And it's tackling a slightly more complicated form of this problem, which is conditional density estimation, which, as you might guess, the goal of that is to learn P data of X conditioned on some external labels Y. Okay? So if you want an example, you can think of this as like in what Gregor showed today with the MNIST, right, digits. Y could be 0, 1, 2, 3, et cetera. And we want to learn the probability density or the distribution of all the 1s. And then all the 0s and all the 3s, like as separate things, right? So that's the conditioning. Okay? And of course, as Gregor said, it's better to learn it as one thing rather than just 10 separate density estimators, one for every digit, because it can share the weights between the different digits. And so it can learn, even though it's trying to learn p of x conditioned on 0, it can learn from p of x conditioned on 8. It can share the information. Okay. Good. So there's a sort of a semi-classical approach to conditional density estimation, which combines neural networks and Gaussian mixture models, which is kind of cute. Looks like this. So basically, I say that all the parameters of my Gaussian mixture models, all the parameters of my Gaussian mixture model that I had before, okay, are functions of y. And I use neural networks to parameterize these functions. So NA, so these are all neural networks. Okay. So if you like, the real model that I'm learning here now is not just p of x conditioned on y, but is p of x conditioned on y. And I guess, let's say the neural networks have parameters, right? So let's say this has parameters theta, this has theta n, let's say. This has parameters theta mu. Oh gosh, I have a lot of indices. And this has parameters theta sigma. Okay? So all the neural networks have parameters. And so what I really am doing here then is minimizing this, or I mean, I have a density which is a function of x and also y and theta. Okay? And then again, the loss is going to be sum minus log p of xi conditioned on yi theta summed over the data. Okay, and the goal is to minimize this with respect to theta. Okay, so this is called a mixture density network. Yeah?
So what is y? So y is another theta.
Y is part of the data, and think of it like a label. Yeah.
What is the role of theta here?
Theta parameterize these functions. These are now functions. So before they were just parameters, right? The locations of all the centers. Now they're functions. Now where the center is can depend on the label. Yeah. So, you know, it makes sense like if I'm trying to do zeros, maybe the center is here. But if I'm trying to do, what's another example? Well, if I'm trying to do nines, maybe the center of gravity is shifted up a bit or something. So where the center is depends on, and the width of this, you know, and the normalization can depend on the label. Yeah. Good. Any other questions? Okay. All right. And then, okay, so these are all classical and like a mixture of classical and neural networks. And then the last, I mean, this is not a comprehensive list, but just to give you a flavor of some of the things that people had used before what I think is still the state of the art. So this is what I would say modern machine learning and state of the art. Was there a question? Okay. No. Okay, so these are very powerful, and they're very expressive because they're really based on neural networks and some powerful mathematics. And of course, the downside is they're not as easy to train or implement. You have to, you know, spend a lot of time on a GPU. Okay, so now let me explain to you what a normalizing flow is. Okay, so the idea of a normalizing flow is to, learn an invertible map between data and noise. So Gregor already introduced the concept of when we're doing generative modeling. We want to start from random noise that follows a pre-described distribution, like Gaussian random noise or uniform random noise. And we want to map that noise to the data space. And that's how we get random outputs, okay? And so that's also the idea behind normalizing flows, is that we want to take the data x, okay, and we want to learn a function f, which maps the data to a latent space. Okay, so this is data, and this is noise. Okay, and it'll also be called a latent space. Good. So I'm not sure Gregor went into any detail, but did you describe the noise, like the properties of the noise for a GAN in any detail? Can be normal distributions, but also it's very common to choose a smaller latent space than you have in the data. Let's say the data is 1,000,000 dimensional, like a megapixel image. It might be common to try to model that with just 1,000 dimensional latent space. Is that going to work here? If I want this to be an invertible map, okay, that's saying that the latent space should have the same size as the data space. Okay, so x, if x lives in RD, then z should also live in RD. Okay, we want this map to be invertible and bijective, so we can run it this way, and we can also run it this way. If we really did have such an invertible map between the data and the noise, okay, so the noise follows a simple distribution. For example, Gaussian or uniform. Okay? So the noise follows a simple pre-prescribed distribution, like Gaussian or uniform. People usually pick Gaussian. So this distribution is called the base distribution. Okay? And if you really did have this invertible map, now think about what you could do with it. So if I take a data point and map it to noise, map it to z space, okay? Remember, probability densities are densities, right? So they satisfy this equation, right? By the way, I hope you got a flavor, like in the GAN story this morning, and also in today's lecture, that like modern machine learning actually has a lot of a formal aspect to it, which I personally like. So there's actually quite a lot of interesting sort of applied math being done here. I mean, it's not like algebraic geometry or anything, but yes?
So I just wonder what criteria between the classic, semi-classic, and modern.
Modern just means supercharging things with neural networks. Yeah, that's how I'm using. Increasingly, maybe we're guilty of this, like propagating this terminology increasingly, but you'll see the idea of modern machine learning. It's sort of a synonym for deep learning, but also like interesting applications of that, I guess. So it's cool stuff you're doing with neural networks, I would say. Yeah.
Are you including Jacobian factor in how the P of Z?
Good. So no, this is a true equation, and then if I want to get P of x, all I have to do is include the Jacobian factor, right? So dz dx. Right? So this is the Jacobian, and I'm saying z is equal to f of x. So it's the Jacobian of this transformation, right? Okay? So that's just, okay, good. So if I can map a data point x to P of f of x, and then, sorry, so let me be really explicit. This is P data, and this is P base, right? Okay, So what does that tell me? If I can map x to a point in the base space, right? If I can take this data here, let me draw it like this, and then I can just map it to, I guess, Gaussian latent space, like that. Then what do I have here? I have what I want. I have the density, right? So the base density is known, right? So let me be super explicit. This is like the normalization factor times e to the minus f of x squared over 2, right? If it's a Gaussian base distribution. And then I can evaluate this Jacobian if I know what f is, right? So x mapped to z, that's, here, let me write, well, yeah, that's density estimation. That's the problem I wanted to solve. For every data point x, I can tell you its probability density. Okay? And what about z goes to x? What's that? Since it's invertible, I can go the other way. So I can start from noise and map it to data. I can sample from noise, right? I can draw samples from the Gaussian distribution. I can make a nice smooth, histogram or whatever of all the z values. They follow a nice Gaussian distribution, right? So then what am I doing when I map z to x? So going from x to z is density estimation. Going from z to x, noise to data, is what? Good. So that's generative modeling. So that's the really cool thing about normalizing flows, if you can get them to work, is that if you have this bijective map, it's very powerful, because you can do both density estimation and generative modeling, which, yeah.
Sorry, why is it called noise?
Because it's random.
But it's not really random, right? It contains the same amount of information of the data net.
Yeah, but its distribution is random. I mean, sorry, its distribution is, well, I guess it's noise like uniform random, or white noise is like Gaussian random, right? So it's like, that's why it's called noise. F actually contains the information about the data. Yeah, yeah. Z is just, totally vanilla random noise. Good. Okay, so, and yeah, so based on this key insight here that we saw in the simpler approaches, the way we train this normalizing flow is the same. Yeah, we want to, I just erased it, but that was the idea, is we do the log likelihood of the density estimator itself. Okay, so train, we'll want to minimize the loss, which is minus log p of x given theta. The parameters, so f here is going to have some parameters. Parameters of f. Okay, and this is what we want to minimize. Yeah, I mean, this is p of x given theta. Is this thing here? Okay, with p x given theta equals p base f of x times the Jacobian. Okay. Now, good. So that's the easy part, is describing what our dream is. Okay. Now the hard part is, how do we realize this dream? In other words, how do we parameterize this function f? Okay. So how to parameterize f. So it's got to be invertible, right? Okay, it's got to be invertible. And this Jacobian, so think about how we minimize this thing, right? What does it mean? We do gradient descent with mini batches, right? Every time we update the weights with a mini batch, we have to calculate the loss or the gradient of the loss, right? So what's the computationally expensive part of that, if this is the loss? So this thing is basically log of this thing is the loss. So what's the computationally expensive part of calculating the loss or the gradients of the loss? Think x and z are both, like a million dimensional. This Jacobian is a determinant, right? So this is a d by d dimensional determinant. Okay, and the computer scientists will tell you that calculating a d by d dimensional determinant generically takes order d cubed operations. Okay, so this is the bottleneck, yeah? So we need a family of invertible functions with tractable Jacobians. So here tractable means hopefully something less than order d cubed operations. Okay, good. And right, so let's tackle the tractable Jacobian first. Okay. So how do we get a tractable Jacobian? So I told you that the CS people tell us that calculating the determinant of a generic d by d matrix is d cubed operations. But what if we make this somehow not a generic Jacobian matrix? Okay, so there's a family of matrices where what if I told you there's a family of matrices where you could do this in order d operations, for exactly d operations? What would that family of d by d matrices be? So family of d by d matrices where the determinant takes order d operations. So what would that family be? Oh, good. Okay. All right. If we made this thing diagonal, let's try that. So, so for example, diagonal would be like, so how do I want to describe this? Yeah. So this would be like f1 x1, maybe okay. It would just be f1 prime fd prime, right? Something like that. And everything else 0, okay, actually that tells us that this has to just be a function of x1, and then all the way down to this just being a function of xd, right? So, good. So this has to be just a function of x1. This is just a function of xd. Otherwise, these would not be 0, right? So yeah, so this is a family of d by d matrices that has a determinant that can be calculated in order d time. But this is not a very expressive family of functions because I would be mapping only x1 to something, only x2 to something, whereas in general my data could be highly correlated in the features, right? So just mapping xi to zi is not expressive enough. Now, does anyone see how to make this more expressive? Yes? Very good. Okay. So we can accomplish the same order d operations while filling this in. Okay, and that's the magic, or that's the brilliant insight behind, that's the brilliant insight behind a family of normalizing flows, which are called, I guess this is just one type of normalizing flows, but this is called auto-regressive flows. I'll explain what that means in a moment. But yeah, so if you make this Jacobian transformation lower or upper triangular, then you make it traxable, and you've specialized yourself to a particular family of normalizing flows called autoregressive flows. Okay, which is what we're going to focus on now, because these are a very powerful family of density estimators. Okay, and so just like here, where we use the fact that it's diagonal to conclude that every f here had to be a function only of its own x, what does the fact that it's lower triangular mean? If you think about it for just a little bit, you'll realize that what it means is that f1 is a function of x1, f2 is a function of x1 and x2, f3 is a function of x1, x2, and x3, etc. Until fd is a function of all of them. Okay? Yeah. So that's how you get the upper triangular, or whatever, lower triangular Jacobian. Okay? And then the determinant, so the determinant is product along the diagonal and is just order D. Okay. Good. And so we need a family of, we still need to specify what these functions are. Okay, but if they have this triangular structure to them, then the Jacobian is under control. And so many choices for form of the f's, or the f, what index should I give this? Well, the f's, okay? Many choices for the form of these f's. Let me just show you one choice, which tends to work pretty well, okay? So for example, here's one choice. Let's let zi equals some coefficients, basically a linear transformation. xi plus mu I Okay, so this is an example. This is called the affine transformation. And there are other choices that you'll find in the literature. But yeah, that's probably the simplest one, is the affine transformation. Okay? So this is a invertible transformation. You can check that it's invertible. I mean, it's kind of obviously invertible as long as this coefficient is not 0, right? As long as it's not 0, I can invert it, yeah? Good. And then, okay, so that's basically how you define, one way you can define a normalizing flow. And then, so what are these alpha i's and mu i's, finally? That's the last thing, right? So these are functions of these coordinates, okay? These are functions of these coordinates. And the last thing I do is to say that alpha I, mu I are given by neural networks. For example, dense neural networks, okay? So that'll give me an expressive set of fitting functions, or coefficient functions, okay? And then I'll have my normalizing flow. Okay. Good. So what I've just described here, this linear transformation with an affine transformation, well, it doesn't have to be affine, but yeah, this is called a made block. Okay, MAID stands for, I don't know why it stands, but it stands for Masked Autoencoder for Density Estimation. And it was in a paper of that title. But yeah, this structure here I've described is one MAID block. Okay, so if I draw that schematically as a MAID block, I will get Z's out of X's, right? Doing this procedure with neural networks. Yeah? Now, I could stop there, but if there's one thing you've learned about how we build deep learning networks, is that we should always think about whatever it is we can do once, we should think about doing it many times, because why not? We can get a more complicated transformation that way. So in fact, the reason this is called a normalizing flow is that we can now consider doing this many times. Each time it's an invertible transformation. Okay, each time it's an invertible transformation, and maybe by chaining together multiple ones, we can flow more accurately to the base distribution. Yes, please.
So because of the connectivity of this at the first time
Mm-hmm.
is limited by the this connection is limited by the upper pressure state called the bottleneck calculation, right?
Mm-hmm.
Then to avoid this limited network, then you increase these layers, right?
Mm-hmm.
That's the reason that you increase the layers. If I think it's pretty connected, and if my computer can calculate this Jacobian very efficiently, I don't need to increase the layers.
Well, I think the reason I think you need to increase the layers, maybe it's the same thing you're saying. The question is, why do I need to increase the layers and do all this, right? Why can't I get away with one MAID block? I think, at least for the affine, probably any transformation you choose, it's insufficiently expressive, okay? It's because we have to choose some simple function here whose derivatives we can easily evaluate and is like obviously invertible. So that's like the building block. But that restricts us to, I mean, who said it had to be just linear, right? So if we want to get something nonlinear between xi and zi, we have to do this multiple times. Yeah.
Because of this approximation theorem, then I just need one layer, right?
No. Okay, good. So the question was, what about the universal approximation theorem, right? So that applies to these coefficient functions, right? So in principle, that will give me arbitrary dependence on the I-1 x's here. But the ith one is still just an affine, simple affine transformation, right? So the universal approximation theorem doesn't buy me anything for the transformation of xi to zi. That's just a line. So it's very strong bias there, very strong restriction there. Yeah. Yep.
I don't understand this because x was drawn from some distribution.
Mm-hmm.
And MAID is mapping this on a Gaussian distribution.
Oh, yeah, good. So, no, yeah, so if I, no. So good, that's an excellent question. So if I stopped here, that would be the Gaussian distribution. But if I chain these together, these intermediate ones don't have to be Gaussian.
No, I mean, this takes the Gaussian distribution and then maps it on.
Yeah, if I stopped here, that would be true, right? But if I keep going, the only thing that's asked to be Gaussian here is this one. This is just some general invertible map. I've done something to my data, but it doesn't, I'm really only putting in the information that it's Gaussian here, right? Because the way I'm going to evaluate this is by multiplying together all these Jacobians, and at the end I'm going to have the base distribution. That's when I put in that it's Gaussian. That's right. Yeah. No, that's very good. Okay. Okay, and actually let me describe how you would invert this to make one more point. Okay, how would I invert this? So, so to calculate this thing, I can think of this as, if you like, I can think of alpha as a big vector, mu as a big vector. And then, so the output of these, once I have the alphas and the mu's, I can calculate all this in one go, right? So I could think of this as D neural networks, right? This I runs from 1 to D, right? So I could say that there's D neural networks here. But remember, GPUs are optimized for matrix or vectorized calculations. So I could just think of this as one neural network with D outputs. Okay, so this is one neural network with D outputs. And mathematically they're equivalent, but computationally on a GPU, it's better to calculate one neural network with D outputs than D neural networks with one output. It takes about the same amount of time. Oh, no, sorry. You save a factor of D when you do it this way. Okay. So, which is to say that when I define this density estimator like this, so going from X to Z, this direction is fast. Okay? And what this defines here goes by the name of a masked autoregressive flow, or MAF. Okay, this is the structure of a masked autoregressive flow. It's called the masked autoregressive flow, if you want to know, because to define this structure of the neural network, you know, each output of the neural network can only depend on I minus 1 of the x's. So the way that they achieve this in these MADE and MAF papers is to apply a binary mask to the, a 1 or 0 mask to the, it's like dropout, yeah, but a predetermined dropout that's either 1 or 0, yeah. Fixed dropout, and it's just part of the architecture of the neural network. They figured out, oh, they realized, oh, we can do that sort of quickly. We don't have to spend any compute on doing that. Yeah. Okay, so that's called a MAF. Now, how do we go this way? Okay, so it's actually non-trivial, right? So the first step, let's see, the first step I should write this as x1 equals z1 minus mu1 over alpha 1. I just inverted the first equation there, right? These don't depend on anything by construction, okay? So they're just constants, yeah. Now I can do x2. Oh gosh. So you have to imagine now doing x2, which is z2 minus mu2 of x1 over alpha 2 of x1, okay? And then I have to plug this one in with x1 plugged in, etc. Okay, I'm not going to write out the rest. So look at how we have to do the inverse. I can't do the inverse all at once. It takes me d steps to do the inverse. Okay, so the inverse, this takes d serial steps. The forward direction I could do in d parallel steps, as thinking of it as one big neural network. Here, with a mask. Here I have to take d serial steps. So going this way, this is called the inverse autoregressive flow, and this is slow. In fact, this tells you how slow it is. It's d times slower, okay? Which, if d is 1,000,000, starts to add up. Okay. Any questions about any of this yet? Let me pause for a moment, see if there's any questions. No? Okay, let me add a couple of comments to this. The first is that there's another thing we can imagine doing in between these steps, because maybe if I literally just did this, then x1 is always treated very poorly in the story, right? So one thing that you can also add to this is permutation. So z1, you can then permute the order of the z's, so that which one is called the first one changes. And then you can permute again. So you can put in shuffling or permutation layers in between each one. So that's something we pretty much always do. Okay. And let me just make one more comment about, in case this affine transformation is hard to grasp or confusing, I just give you one more perspective on it. Okay. So maybe it's easier to actually look at the inverse of this. Okay, so x1 is equal to z1, let's say some beta 1 times z1 plus gamma 1. Okay, x2 is equal to beta 2 of z1 plus gamma 2 z1. Okay, I'll write out just this one. So that's the inverse direction. Okay, and what do we recognize here? So if we were just stopping with one layer, like Thomas was saying, so these are now Gaussian, oops, that's a 2, that's a 3. Okay, so then these are just Gaussians. Okay, then what do we recognize here? So like, let's take this one. So then the distribution of x1 is just a Gaussian with mean gamma 1 and width beta 1, right? Normal distribution with mean gamma 1 and width beta 1, right? And then the distribution of x2 would be a Gaussian with mean gamma 2, which is a function of z1, and beta 2, which is a function of z1. So what we're really doing here, I guess you could say, is each step here is conditioned on the previous step. Okay? So the first step here is learning p of x1 is given by some Gaussian. The next step here is learning p of x2, which is conditioned on x1. And the next step is learning p of x3, which is conditioned on x1 and x2. Yeah? And it's assuming something strong about the form of these probabilities, that they're Gaussians, right? So actually, every step is like a mixture density network. If I were to stop with one made block, every step would be a mixture density network. And if these p's were fully general, I would have the full answer, right? Because now I can just multiply all these together. So what I really want is p of x1 dot 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 xd, the joint distribution. And I can think of this as just a little bit of math to convince yourself that this is the product of these conditionals. x2 condition on x1 and product of x1. Okay, so the joint can be obtained from the product of the conditionals. So that's why this is called autoregressive. Autoregressive means you're trying to figure out the next coordinate starting from the previous ones. Okay. Good. Okay, where are all my notes? Good. Okay. So now let me tell you about some applications of normalizing flows to high energy physics. Yeah? Okay. And there are quite a bit. Yeah.
Shouldn't I just forget about my initial and my final distribution? Treat x as z as x and s as z would be the same as I did for the orbital.
Exactly. So that's the way I wrote it here, actually. So everything here is a function of z, right? Yeah. So I think what you're asking is correct. The question is, can I just think of the inverse flow as the forward flow, but I swap x's and z's? And the answer is absolutely. That's what I've written here, okay? And so if these betas and gammas are neural networks, then what we've defined, this is the IAF. Okay? And so this is very fast to sample. Oh yeah, so, okay, so what I wrote is fast. Yeah, thank you, I almost forgot to make this point. What I wrote is fast and slow is if I have the math structure, where the transformation is parametrized in terms of the x's. If instead the transformation is parametrized in terms of the z's, like here, I have a different thing. I have another paper in the ML world called the inverse autoregressive flow. And for this, sampling is fast and density estimation is slow. So you can't have your cake and eat it too. Depending on how you define things, one direction is slow and one direction is fast. Thank you. Okay, so let's talk about some applications of normalizing flows to hep. And actually, I prepared a list, which is going to be incomplete, but the things I will mention are roughly in chronological order. Okay, I think they're in chronological order. So I think the first application of normalizing flows to hep actually is in lattice field theory, okay, where one of the fundamental computational things they need to do, problems they need to solve, is learn to sample high-dimensional field configurations from the Euclidean path integral. Okay. And I guess for this problem statement, we are told that, I've never done any lattice calculation myself, so we're told that P of x, which comes from this Euclidean path integral, P of x is cheap to compute and expensive to sample. Okay. So given some field configuration, they can tell you what the probability density of it is. But it's very expensive for them to produce field configurations that follow the probability density. Does that make sense? So to sample this P of x, they have to do some very expensive Markov chain Monte Carlo thing that I don't know much about. Okay. And so if you want references, it'll take me too long to write them out, but I'll upload my notes that have all the references, okay? But people in 2019 had the idea, which is to fit a normalizing flow to the true, okay? So they had the idea that given some normalizing flow, I can sample from them. Okay, I just told you it might be expensive to sample, but it's still cheaper than this thing, okay, than the Euclidean path, than what they would have to do with MCMC. So given a normalizing flow, sample relatively cheaply from it, some field configurations, plug them into the true one, and then come up with the right loss term, basically the KL divergence that Gregor told us about, to measure how far away the samples here are from the true distribution. So that's what fit here means, okay? And so they showed how you could do this in some phi to the fourth theory context. And I think that's That's the proof of concept that we have from lattice. Okay, this was in 2019, and it was the first, I think it was the first application of normalizing flows. Yeah, okay. So another thing which came out in 2020 by myself and Ben is applying normalizing flow to do anomaly detection. And this will be discussed in the last lecture. See Lecture 8. Okay, so we're not going to talk about that now. Okay. Shortly at almost basically the exact same time, two groups explored the application of normalizing flows to importance sampling, which is a smart way to do Monte Carlo integration. And let me just briefly describe. So in, say, Sherpa or MadGraph, you always want to, in our field, basically, you always want to calculate this integral over high dimensional phase space and some matrix element squared, right? So we want this. So let's just think of this in more general terms as some d-dimensional integral of some positive function over some volume. Okay? And the dumbest thing you could do in terms of Monte Carlo integration would be to, so basic Monte Carlo integration would be to sample xi uniformly from V. Okay, if I sample xi uniformly from V, this is like just the sum of these xi's over however many samples I do. And if I want to get the right normalization, I should put in this factor. Okay, so this is like a uniform, basic Monte Carlo sampling way of doing this integral. Of course, this is a bad idea in general, especially for high dimensions, d, because it's very sparse. It's not going to cover my phase space very well. And also, it's inefficient, right? If f has long tails or is sharply peaked, most of the places I sample, f is going to be very small. I'm going to waste a lot of time sampling like tiny corrections to my integral that I don't care about. Okay, so this is inefficient and probably not very accurate. Okay, so instead, what we do is called importance sampling. Or not what, I mean, instead a better approach is to do something called importance sampling. So the idea of importance sampling and this is the idea behind C, for example, there's something called the Vegas algorithm, which is used in all these programs like Sherpa and MadGraph. The idea behind importance sampling is to say that okay, so instead, suppose we sampled x from some probability distribution, p of x, okay? Then the integral that I want to evaluate looks like, so I should write this as like this, okay? And then this is f of xi over p of xi. Sorry, so where xi is sampled from p of x. Okay, so I told you in lecture 1 that this sampling relation would be important, and as you can see, I'm using it a lot. Okay, I'm converting integrals to sums and vice versa a lot. Okay, so what's the best choice of p of x? That'll give me the most efficient integral. Well, actually, I don't know if it's the most efficient. Well, okay, I think, yeah, the most efficient integral also minimizes the uncertainty, which I haven't told you about, or the error. But what's the, just intuitively, what would you guess is the best choice for p of x? Yeah, okay. So indeed, you can show that p of x which is just f of x, is the best choice. Okay, and so people had the idea two different groups had the idea in 2020 to say, let's train a normalizing flow to learn basically f of x. Okay, and it's again the situation, so f of x is the phase space factor and times m squared, okay? So it's again the situation where it's cheap to evaluate f of x, but expensive or impossible to sample from it, okay? So it's just like the lattice thing, all right? So the normalizing flow idea is to fit P and f of x to f of x. I would say it's the exact same idea as lattice. Okay, so it's the same sort of problem in a different guise. Okay, any questions about that? So they demonstrated this, I think, in these works from 2020 on some W plus jets processes and showed some gain over Vegas, like factors of a few, depending on the number of jets. So that's the proof of concept right now. Okay. Good. So there have been other attempts to apply normalizing flows to problems like unfolding, parameter inference, effective field theories, scanning parameter spaces, uncertainties. Okay, so I'm not going to go into any detail about those. What I wanted to get to was the same topic that Gregor covered, or started to cover in his lectures, which is so many other applications. But what I think is one of the best applications of normalizing flows, besides anomaly detection, which is close to my heart, is surrogate modeling. Okay, so what's surrogate modeling? This is a different problem statement than what we've seen, where P of x is cheap to compute, but expensive to sample. In surrogate modeling, it's a general machine learning task where the samples are, well, where P of x is not known at all. Okay, so P of x not known. And the samples are expensive, but not too expensive. Okay? So we can make samples, and it costs us a lot of compute. And the goal of surrogate modeling is to fit a model, a generative fit P of x to samples and generate quickly, generate more quickly. So in this case, it's normalizing flow, but in general, it could be a GAN or a VAE, could be any machine learning model. Okay? So we fit some machine learning model to the samples, okay? And then we can generate from those more quickly than from our original way of generating them, okay? So just to maybe be concrete, so I think one of the prime examples of this is, have you all heard of Géant before? Has anyone who's not heard of Géant before? Okay, no one's, I should have asked it the other way, yeah. Okay, so Géant is this package that is super accurate a priori simulations of particles interacting with matter. So if I have some particle interacting with a block of material, like a detector, and the particle is going to shower and propagate through this thing, have a lot of radiation. So Géant can basically, it's an all-purpose, general-purpose modeling simulation package for that. Okay, and it really, as far as I know, it models things at a very, very high resolution level. So it's very slow, but also very accurate simulation package. Okay, and it's the de facto, I mean, it's the standard, it's what everyone uses in, I think, a wide range of experiments from the LHC to cosmic rays to neutrinos. Yeah, it's always something like Géant. Okay, so this is very slow, but accurate. And so the idea or the hope of surrogate modeling here would be, let's pay the price of doing Géant. Okay, so for the LHC, you might need to generate, you know, 1 trillion Géant showers or 1 billion Géant showers. Okay, and that's a big bottleneck. So the idea is, what if we could generate a smaller number, maybe like 100,000, fit our surrogate model to that, and then generate the other billion that we need using the surrogate model. So that's the hope. Okay? And let's see, when am I supposed to stop? In 3 minutes? Okay. Yeah. Okay. Yes.
Can I ask a question? Because I don't understand about this from sampling. In terms of the training, so let's assume that we have a simple, really sharp data function, not that like a Gaussian very sharp.
Mm-hmm.
I want to integrate this out, right? But to do this, below this rest flow, I need to train. I need sampling to train, right?
Mm-hmm.
Is this just same? How can I sampling according to this very sharp to train? Because sampling is very also difficult, right? So I need that the training is very difficult.
Right, so good. So I think, so the way you're going to sample is from the flow and not from the, it's impossible, or very slow or impossible to sample from the original, the truth thing. So you're going to sample from the flow instead. And if it converges fast to the truth, then pretty soon, after a few training epochs, you're sampling from something that's also sharply peaked.
But I need the data, training data. How can I get the training data?
No, actually, so that's the point. You don't need training data here. So the flow generates the training data. And then you plug the training data into the f of x, which you know, or which is, that part is the cheap part in this problem. So you have the integrand. You have the thing you want to integrate, right? And given a data point, you can plug it into the integrand and get the value of the integrand. So you use the flow to generate its own training data. Yeah. And then you measure if the training data follows the true distribution using this KL divergence. Yeah, it's, I guess that's the clever step, yeah. Okay. Well, I didn't get as far as I wanted, so I guess I will pick up next time telling you a bit about fast calorimeter simulation and normalizing flows. And then I'll see what time we have left for anomaly detection. Yep, okay. Mm-hmm.
So we have this tutorial for the normalized flow.
I guess you'll have to ask Sunghak. Hopefully.
So the hydrodynamic simulation in cosmology is probably more complicated and time-consuming than Xiang. Do you know any cosmology?
Yeah, that's the obvious one of the, yeah, so good. So how could we apply this surrogate modeling to hydro sims of the universe? The problem there, you know, that's why I said the samples are expensive, but not too expensive. Like we still need to be able to generate like 10,000 or 100,000 samples to fit one of these things to. And how many universes have they generated, or galaxies have they generated using these hydrosims? I think it's on the order of 10. So, yeah, so that's the bottleneck, yeah. Now, if somebody could figure out a way, if they're inside those simulations, there's a step which is a bottleneck, then so you don't have to run the whole thing, but you could just do that step over and over again. You know, that's how I could see this getting accelerated. But I don't know enough about those things to say more. Yeah.
Questions from the audience in Zoom? Okay, so if not, then let's thank Professor Shih again, and we come back at 3:15.